Okay, so today we're going to talk about problem 3 in IMO 2009. So problem 3 in IMO 2009. So this problem was proposed by USA, and the author of this problem was Gabriel Carroll. He's a perfect scorer. He got a perfect score in IMO in 1999 and is currently an economics professor at Stanford University. So let's have a look at this problem and see how we can possibly tackle it. So the problem says, suppose that S1, S2, S3, and so forth is a strictly increasing sequence of positive integers, such that the subsequences SS1, SS2, SS3, and so forth, as well as the subsequence SS1 plus 1 and SS2 plus 1 and SS3 plus 1 and so forth, are both arithmetic progressions. Now the goal is to prove that the sequence S1, S2, S3, and so forth is itself an arithmetic progression. Okay, so the way we're going to approach this problem, we're going to split it into 3 parts. First, we're going to try to understand strictly increasing sequences in general. We're going to understand what it means to be an arithmetic progression, and we're going to understand alternating arithmetic progressions, because in this question we have 2 arithmetic progressions and they alternate, meaning the first one in the one progression is less than the first one in the other progression, but it's less than. So that would be arithmetic progressions A and B, such that A1 less than B1, less than A2, less than B2. That's what we mean by an alternating arithmetic progression. So that would be the first part. The second part, we're going to identify the important objects and quantities in this problem, and we're going to understand the relationships between these objects. The third part, we're going to examine these relationships and arrive at the conclusion. Basically, we're going to examine all these relationships and then realize that they can only happen if the initial sequence S1, S2 is an arithmetic progression itself, which is the conclusion of the problem. Okay, so first we're gonna study strictly increasing sequences of positive integers. So those are sequences A such that A1 less than A2, strictly less than A2, strictly less than A3, all the way. In general, AN is strictly less than AN plus 1. But more importantly, these numbers are integers. So if A2 is strictly bigger than A1, it has to be at least 1 more than that. So it's bigger than or equal to A1 plus 1. Similarly, A3 is at least A2 plus 1, which in turn is at least A1 plus 2. That's because A2 is itself at least A1 plus 1. So in general, AN plus T is at least AN plus T minus 1 plus 1, and that is at least AN plus 2 plus T minus 2 plus 2. Basically, each time you go down in the sequence, the value is going down by at least 1. In particular, if we're going down from AN plus T to AN, then the value is going down by at least T. That can be rewritten as an plus t minus an is at least t. Or equivalently, for any m strictly bigger than n, we know that if a is a strictly increasing sequence of positive integers, then am minus an is at least m minus n. Next, we move to the definition of arithmetic progressions. So an arithmetic progression is a sequence such that there is a constant d, positive integer, such that the value of the term am plus 1, the next term, is always equal to the value of the term itself, an, plus the constant d. In particular, if the arithmetic progression starts with the term a1, then the second term, a2, is just a1 plus d. The third term, a3, is the third term, a3, is a2 plus d, which in turn equals to a1 plus 2d. More generally, the nth plus 1 term is equal to the nth term plus d, is equal to the n minus 1th term plus 2d. In general, going down from the n plus 1th term to the nth term, you lose exactly an amount equal to d. Now, stepping down from the n plus 1th term all the way down to the first term, the difference has to be equal to the number of steps you took times d. So this is essentially the description of arithmetic progressions in positive integers. Next, we're going to move to, we're going to attempt to understand alternating arithmetic progressions. So those would be sequences where, so those would be arithmetic progressions a1, a and b, such that a1 is less than b1, is less than a2, is less than b2, and so forth. So we're going to try to understand what it means when two arithmetic progressions intertwine. So the first element is the small, like a1 is less than b1, but that is less than a2, less than b2, less than a3, less than b3, all the way to infinity. So how can we describe those objects and what can we learn about them? Now this is important because in the question we have this the arithmetic progression ss1, ss2 all the way up, and then we have another arithmetic progression ss1 plus 1, ss2 plus 1, and so forth. And what we know is that since S itself is a strictly increasing sequence, this number is less than this number, which is also less than this number, less than this number, less than this number, less than this number, all the way up. So the question itself presents an alternating arithmetic progression because this is an arithmetic progression and this is an arithmetic progression. So it's important before we tackle this problem to understand how alternating arithmetic progressions behave. Okay, so in this part we're going to try to understand alternating arithmetic progressions. Now, the setting is that you have an arithmetic progression A and an arithmetic progression B, such that A1 is less than B1, is less than A2, is less than B2, all the way up. But also, both are arithmetic progressions, namely, there exists D and D prime, such that D equals, so constants, D and D prime, such that D equals an plus 1 minus an, that's the common difference, and then D prime is bn plus 1 minus bn. That's what makes A and B arithmetic progressions. But they're alternating because they satisfy this property. Now, the main thing we need to understand about these objects is that if they're actually alternating, then it should be the case that d is equal to d prime, and also there's a constant r such that bn is just a shift of an, namely bn is just a constant r plus an for all n. So it makes sense if this was the case and you have an arithmetic sequence a1, a2 all the way, and you shift it up a little bit by r so that it doesn't go beyond a2, a1 doesn't go beyond a2, then you're going to get a new sequence bn that's also arithmetic. Now here we're trying to prove the opposite, is that if both are arithmetic and this condition is satisfied, then it must be the case that their common term is the same and one sequence is just a shift of the other. So there are a few approaches to see why this is the case. We'll present a few of them. So the first approach goes as follows. You can imagine having a savings account and getting a fixed salary every day. So initially you have $A1 in your savings account, and your friend has B1 in your savings account. And let's say D is the amount you're getting every day, and D prime is the amount your friend is getting every day. Now, if D happened to be bigger than D prime, that means you're being paid every day strictly more than your friend is being paid every day. Now, what does that mean? It means even if initially your friend had more money, that means eventually you will have more money on one of the days. Now, the assumption of this alternating sequence is that you have less money than your friend on any given day, but your friend has less money than you if you took your than you tomorrow, basically. So on any given day you have less money than your friend. That's what an alternating sequence is. an is less than bn, but also bn is less than an plus 1. So that means as soon as you get your daily stipend and your friend didn't get it that day, you have more money than them. In particular, if the common term or the daily stipend you're getting is strictly more than what your friend is getting, then you should eventually have more money on one of the days than your friend. On the other hand, if your friend is getting more money than you, then eventually not only will they have more money than you, they already do have more money than you, but they'll have much more money than you. Is going to be even more than you have tomorrow. In particular, if D prime is bigger than D, then eventually Bn is bigger than even An plus 1, which is An plus D. Now, both of these two scenarios are not the case when A and B is an alternating arithmetic progression. In particular, where A and B always satisfy this, An is less than Bn, but Bn is less than An plus 1. Neither of these two cases can happen, and the only possible scenario is when D equals D prime. Okay, another way to see this is the following. So we know An is less than Bn is less than An plus 1, and both A and B are arithmetic progressions. Our goal is to show that there's a constant r such that Bn equals An plus r. Now, if you consider the sequence Cn equals Bn minus An, now this is a difference, C is the difference between the two arithmetic progressions A and B. Therefore, C itself is an arithmetic progression. Now, since Bn is bigger than An, we know that C is strictly bigger than 0. Moreover, Cn is bounded. Why? Cn is bounded because Cn is Bn minus An, but Bn is less than An plus 1. So Cn is at most Bn plus An plus 1 minus An, and that's a constant. That's just the common term of A, namely D. So Cn is an arithmetic progression, right? That is never negative and never too large, right? So imagine having a savings account and every day I'm gonna give you a certain amount. Now, you know for a fact that your saving account, even after so many years, is never more than this fixed amount, D. What can you learn from that? What you can learn is that your savings account never grew, because if it was growing, it will surpass this threshold of D, and if it was going down, it will go below 0. But if it's an arithmetic progression, so every day it's getting the same amount, but it never exceeded either 0 or D, then it must be a constant. In particular, Cn equals R, where R is a constant. Or equivalently, since Cn is Bn minus An, you get Bn is just a shift of An. And that's the other way to see the conclusion. Okay, so this marks the end of the last part of this proof, which essentially is understanding strictly increasing sequence arithmetic progressions as well as alternating progressions. And the conclusion was if A is a strictly increasing sequence and M is bigger than N, then Am minus An is at least M minus N. If A is an arithmetic progression, then by definition there is D such that D equals Am plus 1 minus An. And finally, if A and B are alternating arithmetic progressions, namely A1 less than B1 less than A2 less than B2 and so forth, then Bn is merely a shift of An, or Bn equals An plus R. Now those are all the necessary sort of preliminaries that we're gonna need to tackle this IMO problem. In particular, next we're gonna label or examine the objects in this problem that are going to be necessary to finish the problem. Okay, so in the second part of this problem, we're gonna examine what we're given in this problem and identify the important objects that we're gonna deal with to solve the problem. So first, let D be the common term in the main arithmetic progression. Now, SSN is an arithmetic progression, so there's a constant D, so let's just name it capital D, to be the generic difference, SSN plus 1 minus SSN. And this is true for all n, so if n changes, D is the same. Now, similarly, since the arithmetic progressions SSN and SSN plus 1 are alternating, we know that there is a constant R such that SSN plus 1 equals SSN plus R. So let's just label it R so that we know what we mean when we say R later. Now, let's define the generic difference sequence, delta n, to be just the difference between two consecutive terms. Now, since S is strictly increasing, we know this is always strictly bigger than 0. Moreover, we can show that this sequence delta n is bounded. Why? Well, we know since S is a strictly increasing sequence, then for any A bigger than B, SA minus SB is at least A minus B. But what does that mean? If we let A be equal to S of n, and let b be equal to s of n minus 1, then what we're going to get is the constant d, which is this difference, is going to be at least a minus b, which in this case is Sn minus 1, and that's just delta n. So delta n is indeed a bounded sequence. It's the values it can assume is always something bigger than 0 and less than d, and it's always an integer. So it's natural to consider the extreme values that this sequence attain. In particular, let small m be delta a, where it's the smallest this sequence can take, and let delta b, let capital M be delta b. It's the maximum over all n of delta n. Now, why are these numbers important? If our goal is to show that Sn is an arithmetic progression, then essentially what we need to prove is that delta n is a constant sequence. So delta 1 is the same as delta 2 all the way. But since we know it's bounded, it's natural to look at the smallest value it can attain, the largest value it can attain, and show that they're equal. So next we're trying to understand the relationship between these objects that I identified. So D is the generic difference in the arithmetic progression. R is the shift that takes Ssn to Ssn plus 1. Capital M is the maximum difference in the sequence S. Namely, it's SB minus 1, which is also the maximum across all I of Si minus 1. Small m is the smallest difference. So it's Sa minus 1, which is the minimum across all I of Si and minus Si minus 1. Now these variables impose a lot of structure on our sequence. In particular, we can show that if A is bigger than B, then Sa minus Sb is bounded above by M, which is the maximum difference, times A minus B, which is the number of steps to go from B to A. Now it's also bounded below by M times A minus B. Now I'm going to explain why this is true. Let's start with simpler examples. Let's start when A is exactly B plus 1, or when A and B are consecutive. So when A and B are consecutive, we just have Sn plus 1 minus Sn is at most 1 times M, at least 1 times small m. Now this follows from the definition of capital M and small m. Now, what if the difference was 2? Now Sn plus 2 minus Sn, we can rewrite it as a telescopic sum of Sn plus 2 minus Sn plus 1 plus Sn plus 1 minus Sn. Now each one of these terms is bounded above by capital M, bounded below by small m. So this term is bounded above by 2m and below by 2 small m. Now similarly, Sn plus 3 minus Sn is always bounded above by 3 capital M, bounded below by 3 small m. And we can induct on this, or following the same approach, we can say whenever A is bigger than B, then Sa minus Sb is bounded below by A minus B times M, bounded above by A minus B times capital M. Now there's another thing to note in here, which is, when does the equality happen? If this happened to be equal to this ever, like we know this is at most this, but when would they be equal? And the question is, they're equal. The answer is they're equal if all these small differences, so S of P plus 1 minus Sp, all the way to S of A minus Sa minus 1, all these small differences that built up this larger difference, they have to all be equal to the largest possible difference, capital M, for this equality to hold. Now for this equality to hold, you want the other way around. You want all these differences to be equal to small m. So this relationship is very crucial to solving the IMO problem, and we'll see next how we can essentially wrap up the question. Okay, so this result is apparently sufficient to solve the problem, but in the next step we're going to show the core of the problem. We're going to do the most tricky part of the problem, where everything comes together and the problem is over. So last thing we proved, if A is bigger than B, then SA minus SB is bounded by A minus B times small m and A minus B times capital M. Now if we choose A and B to be Sn plus 1 and Sn, then what we get is D, which is essentially S of n plus 1 minus S of Sn. Sn is also like S of A minus, of the form S of A minus SB, where A and B are these. So this is bounded above by what? A minus B times M, and that is Sn plus 1 minus Sn times M. So what that says is for all n, the thing about this is D is constant, capital M is constant, but this relationship is true for all n. In particular, to get the most out of this relationship, let's choose n so that this expression is minimal, as small as it can get. So earlier we chose A to be the one, earlier we chose A to be SA minus 1 is the smallest difference in this sequence. So if we choose n to be A minus 1 here, then S of n plus 1 minus Sn is going to be the same as SA minus 1, which is the smallest difference possible, is also small m. So what we get here is D is at most capital M times small m. Now this is a strong inequality. Now moreover, the equality holds here if and only if all the small differences that made up this expression, SA minus SB, all of them are equal to capital M, the largest possible thing. So equality here would be if for all I, S of n plus I minus S, like all these differences from this one to this one are all equal to the largest possible number they can be, which is capital M. Now, the cool part about this argument is this upper bound, we can achieve a very similar lower bound using the other inequality. And instead of choosing the minimizer, we'll choose the maximizer. So we'll see what we can get. So D is again the generic difference, and it's at least small m times A minus B, which is in this case S of n plus 1 minus S of n. Now if we choose n to be the maximizer of this expression, namely B minus 1, then what we're going to get is Sn plus 1 minus Sn is equal to the maximum possible value, capital M, and D is at least small m times capital M. Now keep in mind, this inequality along with this inequality, we get that equality has to happen. So equality holds, and also capital D is m times m. Now we're almost done. Let's just examine the equality and see why equality gives us that as an arithmetic progression. So essentially, when equality happened, we said all the small differences have to be equal to the largest possible one, and for equality to hold here, all the small differences have to be equal to the smallest possible one. Now if we look at the very first difference, namely when I equals 1, in one case it has to be capital M, in another case it has to be small m. But in particular, in the one case it has to be capital M, and in the other case it has to be small m. But we know that these two terms are equal, because earlier we said small r is just, earlier we said this arithmetic progression is just a shift of this arithmetic progression, and the difference, the amount of shift you need, is small r. So small r in one case will be equal to capital M, in another case equals to small m, but r doesn't change. So capital M has to be equal to small m. But the way capital M and small m were defined, they were the maximizer of these differences and also the minimizer. Now if the maximizer is equal to the minimizer, that means this sequence is always the same. Its maximum achievable value is the same as the minimum achievable value. And so the difference between Sn plus 1 and Sn is always constant no matter what n is, and hence S is an arithmetic progression. Alright, thank you very much. I hope you enjoyed this problem.